if she was with you. Okay. Can you see this? So finally, right? I mean, you've been waiting for this moment. I don't know if you've been waiting for this moment. You've basically already been stumbling upon the Hodgkin and Huxley model, even as we gave you the resources such as Jack Villiger or explainers or the physiology web, which were the links in our flipped session primarily. But here I want to give you a bit of a motivation for why the Hodgkin and Huxley is a mind-boggling piece of understanding respect to neurons. People originally did not know where the spikes came from, and the Hodgkin and Huxley model was instrumental in making predictions about what were the spike generation mechanisms. For example, that there were voltage activated sodium channels, not only, also that voltage activated sodium channels also inactivated at a high depolarized potential. So those are insights about the functioning of the neuron that up until the 50s we did not have. We knew that neurons were spiking ever since like the beginning of the 20th century with the work of Lapique in 1907. French guy that phenomenologically observed the spikes and said, okay, well, it seems like they're integrating current and producing spikes, but they did not have any understanding of the underlying biophysical mechanisms that were producing, meaning they did not have a theory. It was just a guess. And the Hodgkin-Huxley gave the formal understanding of these mechanisms. And the beauty of it is that it's a very modular understanding. So you can now, to a Hodgkin-Huxley vanilla, you can add new ion channels with other properties that are now derived from a variety of sources in neuroscience. People then inspect what kinds of channels are in the neuron. So the Hodgkin and Huxley model has a very small subset of ion channels, but you can put more and get more phenomenology out of it. So the spikes can get more interesting and complex, because it turns out that in biology, the variability in the spike patterns is one of the most daunting aspects of it. Many of the spiking models that we have these days that can do interesting things are very simplified models that we're going to be talking about in the future, called leaky, integrate, and fire models. Elias is going to explain them to you, and also how to go from the Hodgkin and Huxley into these simplified models. But these simplified models, they simplify away many of the biological phenomena that probably has functional consequences, and we're not taking them into account just because it's hard. It's important that you understand the phenomenology of spiking first, that you appreciate all of the details of like a simple trace, not because that will immediately give you an understanding of what consciousness is like or how that participates in processing, but because that gives you an appreciation for what is to be explained still, right? So with spiky models, there's a lot of very cool stuff we can already do. For instance, we can draw numbers. We can rig it into a robot and having it repeating a sequence. So spiky models are very powerful already in terms of what they can construct. But there is a lot of important biological detail that is seen that they exclude. And the question for going forward in the future, like this is 21st century, like second decade, the questions going forward are which details that we're not including are fundamental to our progress, our scientific progress. So what should we include to go forward? Okay, so this is basically the motivatory, because you're going to be facing nitty-gritty complexity. I give you the hardest model first, because I gave you the neurons, and you're going to go into the lab visits next week, and you're going to see some recordings of neurons and so as well. But I want you to, really, this is the biology for the uninitiated. And I hope you enjoy going through this and discovering all the ways in which you never thought that a neuron could fire before. And we will be discussing more spiking patterns as they go. In the review of this project, I'm going to tell you about multi-compartment models, that is, models that have branches, and what are the consequences of neurons having branches that we learn via the Hodgkin and Huxley model. Other questions of the sort, biological variability, you go into the brain, measure two neurons that look very similar to each other qualitatively, but they produce different spiking patterns. Why? Sometimes you have two neurons that are completely different from each other morphologically. They have different shapes and they produce the same types of spikes. Why? So those are the big questions that now we started to be able to tackle with models such as Hodgkin and Huxley. So I think that this is enough laudatory introduction to the Hodgkin and Huxley model. And they got the Nobel Prize for this. And it is a stepping stone for so many interesting avenues of research. So since in the computing brain, our job is to explain how biology creates computation, you have to start here. Later, we're going to look into artificial neural networks and see what they abstracted away. Then we're going to make some function, pattern recognition, memory, you name it. But for the moment, we are looking into phenomenology so that you know what there is, and so that you understand later what we're actually excluding in the simplified models. Questions up to now? Just introduction, right? Mario blabbering. But I hope that this gives you a sense of why you're going into this. The learning objectives are in the project. And I would like all of these to actually reach the depths of your mind. So read them attentively, both at the start of the project and at the end of the project, to see how many of these I actually got in. Particularly funny things that you might not have cared about, especially depending on your mindset. Stuff like know the physical units of the terms you're using. I can't emphasize this enough. If we're dealing with a physical model, then it's important that you understand how much of what is going in. These are not simply numbers. These are numbers representing physical quantities. So attend to those. And you're going to hear things that are funny, like millisiemens per centimeter square, or you're going to, you're going to get some units that you haven't handled before. Fine, take it easy, and you just let them go in. Siemens, the unit of conductance. Amperes, we've talked about amperes before, but that gives you a sense of scale, right? So units are there for you so that you understand by how much. Is it 1 kilo, or is it 1 gram, or is it 1 milligram? In neurons, these scales matter because this has to do with how much power the neuron produces. For example, you know that a battery has 5 volts, and a neuron produces minus 70 millivolts of amplitude deflections. What's the current that a neuron can generate? Compare that with a battery. This will then, give you a sense of, by how much you have to zap, by how much you have to electrocute a cockroach before it starts moving its legs. Connecting the physical variables with the models will give you a sense of scale. You might not deal with this immediately, but it's something to be aware of, and that's why it's here, and that's why I'm insisting on this. Okay. All of the other ones are basically the assembly steps into the Hodgkin and Huxley model. Now, as I might have mentioned, so in the introduction of the of the computing brain, in the first week, I asked you to watch the videos about the battle between computational neuroscience and neural computation. And I said that the Hodgkin Huxley model was the dawn of computational neuroscience. I think that this is absolutely true. So this is the first time that we felt confident that that we can go forward with a theoretical model. And this theoretical model is purely electronic. On the left, you have what is called a balancing equation. The sum of currents coming in, it basically is the total sum of currents. That makes sense, right? So the sum of sodium plus potassium plus the input current basically are the individual components. And so you see, this is all the current that we have available. When you think about current, think about a flow of ions. It's like water in a pipe. When you talk about amperes, you can think about liters per second, okay? So it's per second, it's a flow, it's a quantity that is flowing. Coulombs are the unit of charge. So coulombs are like liters, amperes are like liters per second. Okay, don't know if that's obvious from any of you, but get your mindset. And so this is how we're creating this metaphor. We think there are currents going in the cell and currents going out the cell, and they have different inputs and outputs. And so this is what's represented by the circuit. The membrane has a capacitance. A capacitance is commonly something that is thought of as the reorganization of charges across the two sides of a dielectric membrane. So there's an insulator, there's something that isolates the charges from inside and outside. And because the positive charges repel each other and the negative charges repel each other, they tend to accumulate along the surface, and then they create a potential. Just basically positive here, negative here, they accumulate a potential. There's no current crossing in the capacitor, okay? So they're just accumulating. So that accumulation basically increases the potential between the two extremes and tries to force through the electrical gradient, tries to force the ions in the direction of equilibrium. But as we talked about in the previous lecture, now you know that the electrophysiological situation is one of the balance between two gradients, the electrical gradient and the chemical gradient. The chemical gradient is dealing with the concentrations of ions. So if there's too much of something on one side and too little on the other side, the too much tries to pass to the too little. It's a little bit like pressure on a balloon. So you open the balloon, ions cross, pressure equalizes. Only that there's not simply air. It's a mixture of, say, 2-3 components forming it. It's oxygen, nitrogen, and hydrogen, helium, I don't know. And so each of them will have different concentrations. And these concentrations are pressing the like out. So this is the chemical grade. The capacitance is dealing primarily with the electrical gradients, basically how many ions. So what species of ions do you have inside the outside? So you have a potential, and you have these little arrows here. Now, so what do you notice about this graph? Now I want to volunteer. I've been talking for a little while, and I want you guys to look at this diagram here and remark upon things you observe. Imagine this is the game of 7 differences. What are things to notice here? Just visually, like what's the differences? What are the differences? So you have, you know, these guys here, what are they?
It's a parallel arrangement of the ion channels, I think, in the circuit.
Exactly. Great first point. Next volunteer.
Oh my God, there's a difference between how the loop channels are represented and the voltage gated channels. Like
very true. So what's the difference, Ella? So I think, can you speak a little bit louder?
Yeah. like the ionic channels are represented as variable resistors, so they have like the like line going across the zigzags, but the lead channels are just, well, I don't know if I can know the I'm forgetting it now.
Yeah, so this
But
is just a
there's a
resistor, and the other ones you can potentiometers if you like, but the variable resistors, so that also works. I don't know if many of you knew this before, but notice the difference that Ella just pointed out between the squiggly line in RL and the squiggly lines in RK and RNA. So in RK and RNA, the resistance is changing. These two are active channels, active ion channels, and this is a passive ion channel. All of them are ion channels. What else do you notice?
That for sodium, the plus and minus is basically flipped compared to the potassium and the leakage.
Very sharp eye.
So the direction is basically different.
So, great point. Now, what are these symbols here? The small and large little bars. What do they represent? Do you see my cursor?
A battery?
Hmm?
It's a battery?
It's a battery, right? So you have batteries of inverse poles. This gives you a sense of the assemblage of the ions and the directions of the currents. You already knew this before from a different perspective, but now you're looking at this from the perspective of the circuit, because the perspective of the circuit gives you the ability to compute the flows and how the potential changes over time. Anyone would like to remark upon something else here that, there are other few little elements that might be worth discussing? What's the big E? The capsule E. What does that represent?
Maybe that's the action potential. I'm just guessing.
Not quite the action potential, but the potential itself.
The potential,
So,
great.
That's what E represents, is me dropping something. So I didn't drop it, it's potential energy. So it represents the distance between the outside and the inside. If you break the membrane, if you destroy the capacitor, then there will be equalization, immediate equalization of this potential, the potential will disappear. The energy in the neuron is in this difference between the inside and the outside, and the fact that it actively maintains it. So it actively maintains it. Now, what else do you notice? Now, we discussed things in the electrophysiology lecture, and there are other things. What other components of the cell membrane don't appear here that you have learned about before? So what's missing in this picture, according to you? Is there something missing in the circuit?
The sodium potassium pumps.
Ta-da! And why are they missing here?
Because compared to the voltage gated channels, they're much slower. So
That's
maybe
right.
they're in the process of the action potentials firing. They don't really make a large difference.
That's it, Rob. Thank you. Now, another something you should realize is that in here, our resting potentials and reversal potentials are defined as parameters. We impose them. So if it's something that I want you to think about. So basically the resting membrane potential that is at about minus 70 millivolts, sometimes also equalized to be 0 millivolts, and you're going to learn about that in the project. But so say this distance between the activation of sodium and the resting membrane potential from minus 70 to say 100. This is actively maintained by the cell, but instead of talking about the mechanisms that actively maintain it in the cell, we just set it as a parameter. I want you to try to get a sense for what that means. I mean, instead of basically calculating the resting membrane potential, we're just defining it, all right? And you will see where it appears in these equations. So, for instance, well, I introduce you to you all the lovely Hodgkin and Huxley equations. Ordinary differential equations, very ordinary. So if it's ordinary, it must be easy, right? Let us look around a little bit and get acquainted with this set of equations. Let's start out with the left side of the master equation, of the balancing equation, so C times V dot. Anyone knows what the V dot represents?
The derivative, right, of V.
It's another way to talk about dV dt, right? Is the change of voltage. So thank you. And what unit has C, capacitance? Anyone knows?
Siemens, you said?
No, I said the conductance has Siemens.
Oh, sorry. Capacitance.
Good one. No, good. I mean, that's exactly what we're working through.
It was farads, right?
It's
Yeah.
farads. Farads. And if you multiply farads times, so what's the unit of V? Like let's start with this. What's the unit of V? It should be very mnemonic. It should be easy to remember. What's the unit of the membrane potential?
Volts.
Volt.
Yes. Unit, yeah, millivolts. I mean, so volts, millivolts. What's the unit of V dot? Or dV dt?
Also volts? No?
Not quite.
Millivolts per second.
Da. Anyone, do you guys see why? We're talking about the change, right? So we're talking about the change over time. It's a little bit like velocity. We're changing the volts over time. So it's volt per second. Now, if you multiply C times V dot, now take a gander, have a guess. What's the unit of this multiplication? You can phone your electrician right now. So remember that was one of the prerequisites for the computer brain. So, like, have a little study of circuits, but you probably didn't attend. You studied it, but you didn't really attend to the units. Now, this is current, guys. You have capacitance times a change of voltage. Capacitance here works a little bit like a dampener. So it basically is a factor that multiplies, so farads times a change of voltage per second is a current, is a number of ions per second. So if I mentioned before that amperes were charge per time, so this is charge per time. And on the right side of the equation, everything sums to a current as well. So you have current on the left side and you have current on the right side. Should be intuitive. And so now that you know that, then you should also be able to slowly start working your way through things like multiplying a conductance times a voltage. Notice that these voltages here are different. They're not V dots, they're just these. What's this V on the right side here of the equation? Anyone can guess?
would
Wouldn't have to
say.
be the
Oh, sorry, you go.
Both of you, okay. Let's speak at the same time. Let's see if you agree or disagree.
go ahead.
So I was gonna say that it's the that is the charge of a potassium ion.
So, it is not. So the V itself is the momentary membrane potential. It represents the state. So that's the state variable. So remember this name. It's gonna come back in the neurodynamics lecture. But what we're talking about here is the state of the neuron. And the neuron has a voltage. You can measure a voltage of the neuron, and that's it, the V. As a function of V, as a function of the momentary voltage, you know whether the neuron is going to depolarize or hyperpolarize. So say, for example, your V is below, for instance, the resting membrane potential. Like in your brain, you should be thinking, well, if it's below the resting membrane potential, the V is below the resting membrane potential, V wants to go back to the resting membrane potential, right? So V is the thing that is measuring the moment, and V dot is by how much it changes. So what this equation is saying is that on the left side is the amount of change of voltage is a function of the voltages, of the voltage you now have in the cell, the membrane voltage, the one number. We all on the same page now?
Could you repeat that last bit? Yes.
So the change of voltage, V dot, is a function of the momentary membrane potential, the state variable, the voltage of the cell, the membrane potential of the cell. So this is the change of membrane potential, V dot, and this is the actual momentary membrane potential. So it's a little bit like saying like this. So your car will accelerate as a function of how fast you're going. And say you are going against air drag, and your car is basically going at 800 kilometers per hour, then air drag is going to push it back until you're like a reasonable speed, airbag and friction. So the change of velocity is a function of the velocity. I hope these metaphors help you forming a picture of what this equation will say. When you work more with it, I hope that it's going to get even clearer. Now, okay. V is then the voltage of the cell. EK is the reversal potential or the equilibrium potential, as Aaron would like me to say, of potassium. That basically means like where potassium wants to go. And this is where sodium wants to go, and this is where the leak current wants to go, and which is usually close to the reversal potential. You will notice that some people use E here, and some people use VK too. And so be aware that there are notation differences. There are as many notations as there are mathematicians. So, get used to look into equations and look at them by form and shape rather than like attend too much in what the things are called, right? Try to abstract away the names of the variables. So here EK, E and A, and EL are the equilibrium potentials for the individual lines. So they're pushing the cell into their preferred direction. More about this in the project. Now, this is the last thing I'm going to tell you about this equation. You see this m to the power of 4? This m cube h? Those are the other 3 state variables of the Hodgkin and Huxley equation. And these are the gating variables. Now, what's a gating variable? So these indicate the proportion of ion channels that are in an open or closed state. Forget the exponents for a moment. Just think about what I'm telling you. M is the activation gate of sodium. So what does it do? well, it is the proportion, like right now it's M, like it's not dot, it's just M, it's the proportion of channels open. So if you have 1,500 sodium ion channels in the axon hillock, and I tell you that 1/3 of them is open, you know that it's, 500 channels are open. But I want you to think about this as the proportion, not as the actual number of sodium channels, but the proportion. So just think here that it goes from completely open, 1, to completely closed, 0. So what happens if M is 0? Here where my cursor is, what happens if M is 0? If, on the other, spoken differently, if all of these sodium channels are closed?
Then the denominator would be 0, or it would be 0.
There's no current. There's no sodium current whatsoever. So if you use a sodium channel blocker and you block all of those and they're all closed, then there's 0 open and nothing can go through sodium. What if I have N equals 1? So all potassium channels are open.
Then you would be able to use that in the function. Like it would have a unit or a number, and it would contribute to the overall.
Then you have, in a sense, it represents the maximum possible current from potassium. All of channels of potassium are open, so you're going to use that in the formula, as you mentioned. So to put conductance of potassium, basically what's the size of the holes, like how many holes there are. It's a total, is a G bar, and you will read about that in the project, times the driving force, V minus EK. Now, M, N, H can be written in the same mathematical form. And I'll tell you what this means. Like, I'll start with, say, let's start with H. H is the inactivation variable of sodium. Here it says that H changes dH dt, H dot. So the change of the proportion of inactivation of sodium, change of proportion of inactivation, right? So channels are inactivating. If H dot is positive, then dH dt is positive. That means the channels are closing. H infinity V is at equilibrium. At equilibrium, I'll come back to this. How many channels are inactivated? So the change of H is how many channels are inactivated, H, minus the steady state inactivation proportion. So put it like this. I have a cell that is really very depolarized, is at a very high voltage. At a very high voltage, H wants to be 0 because he wants to inactivate. It will clog the channel. So H is the inactivation gate, and it says like H is 0 when voltage is high. So make sense this part of the argument? So H is 0 when H infinity of a high voltage is 0. And say now you have H being a very high number because you just opened your sodium channels. So say H is 1. So basically what the equation is saying is that from 1 channels active, you're going to 0 channels inactive via a certain rate, H dot, dH dt. So these are the state variables. You have 4 state variables in the Hodgkin and Huxley model: the voltage change, the change of proportion of open and closed sodium channels, the change of proportion of inactivation of sodium, and the change of proportion of potassium channels. The tau at the denominator is the proportion with which, is the speed with which they're closing. And that's a property of the channels. How fast, they open and close is a function of the voltage and a property of the channel. come and show this to you how these equations look like, and they will be like gloriously in the project in multiple occasions, and I will ask more questions about your understanding of these as you now progress. Questions?
Yeah.
So, oh, sorry.
Thanks,
no,
Joe.
no, just, no, I didn't quite understand it. So you're saying that H infinity, so it represents that equilibrium, how many channels are inactivated?
Yeah,
Because
so H infinity is the steady state for a given voltage. So if you have a high depolarized state, you will have many the steady state where the channels want to go as being very is going towards zero. So basically, the steady state for high voltage is close to zero. I can show you how these functions look like.
well,
but what I want you to understand at first is simply that there is a place where they want to go, H infinity V, a place where they are, H, a speed with which they change, tau.
yeah, I know, I understand, I see that, but just for H, because it's inactivation variable, if H is 1, does it mean that it wants to close them all, or?
Yeah, look at now the current equation. Look up here. So when you have the sodium channels inactive, how much current is going through the sodium channels?
When they're inactive, it would be none, right? So 0 is inactive, in which case. Okay, then I'm with you. Okay.
Okay, so it's a few steps you have to think about. I wanted to give you a sense of the equation. I'm gonna fry a few slides that will come back later. But now I'm just going to finish this part of the lecture so that you can get into the projects. In general, currents coming through ion channels, they have gating variables, which can be of the activation and inactivation gate type. Here in the bottom, in this, there is an example of the sodium channel. And in the sodium channel, you have the extracellular domain and intracellular domain, and the activation gate is this this little ball that clogs if the voltage is too high after the action potential passes, and you open the channel as a function of also voltage. Notice here, G bar is the max. So this, for any current, that is for any voltage activated channel, this is a general way of writing it. Current equals conductance times the proportion of channels letting things through, which is a P, which is a combination of opening and closing the channel or activating and inactivating. So M opens while H closes, times the driving force. So this is the notion of individual currents through individual ion channels. More about this in the project. Let me go forward. I'll take questions in a moment. This is for reference. I'll put this slide online now. It's so that you know what are the concentrations of the ions inside and outside the cell and how we calculate the equilibrium potentials for the different ions. So you just, for the up until now, we simply said that E of sodium minus the voltage is the driving force. Now you see the explicit voltage potentials. Now here for sodium, for instance, you have 2 equilibrium potentials, and that depends on what is the concentration of sodium, or the ratio of concentration of sodium in the outside and in the inside. Outside being the numerator of the ratio, and 5 being the denominator. With me? So these then are your reversal potentials with which you're going to be creating the driving forces. And you compute them because you know what are the differences of ion channels inside and outside. Anyone knows what this A minus here represents? All of the other ones seems like very famous ions, sodium, potassium, chloride, calcium. What's A minus?
So is it a depolarized acid?
So it's a negative ion, so it's an anion, and it is formed by macromolecules, big fat proteins that are negatively polarized, trapped inside the cell, helping keep the inside of the cell hyperpolarized. Right, so these don't go through the ion channels, and they're just negative and happily inside. Sensible? For reference, go back to the slide. The combination of driving forces, that is, one ion is pushing in one direction, the other ion is pushing in another direction. One way you can think about this is that the resting membrane potential is basically proportional to the pushes and pulls of the different ions. The pushes and pulls of the different ions are proportional to the number of channels activated for them. You can compute then the resting membrane potential with this equation. These are the conductances for the different ions at the different given moment. You see here two lines. The top line is at rest, and the bottom line is during the action potential. So basically,
Sorry.
yeah.
Oh, can I ask a quick question? I don't
Please.
understand what these G means. What
That's
are
the conductance. That's the
the
conductance.
conductance?
That's
Okay.
the conductance. So the reverse of the resistance. It's the same G as we had in electrophysiology, luckily this time, in the electrophysiology flipped. And you will see a lot of G's coming in. So basically, this is the number of available holes for ions to cross. So the total cross-section of ion available channel space. Make sense, Milou?
Yes, that makes sense. I was just a bit confused.
Okay. No, a bit confused is good, because then we can unconfuse you a bit, and then it's done. Let's move on. Here, the action potential, the conductance of sodium is enormous. That's because the sodium channel is open. And here, very tiny. So during rest, sodium channels are mostly closed because the steady state of sodium is low. But during action potential, you have this is the trick of the action potential. The more sodium ions come in, the more depolarized the cell gets. The more depolarized the cell gets, the more sodium ion channels open. So that's the positive feedback. That's why then sodium gains and gains and gains and gains until the sodium starts inactivating, in which this G is going to get small again. And then so the resting membrane potential is going to go back into a hyperpolarized state, back to close to minus 70 millivolts. The cell, the neuron, the spike, is in essence a mixture of positive and negative feedbacks. You have the positive feedback of sodium and the negative feedback of the inactivation of sodium and of the opening of potassium channels. So this is basically how you create the action potential. We already read about this before. And now what you're doing is you're supplementing your intuitions about what you read before. More sodium means more sodium means depolarized, more depolarized means open more channels, but then, you know, what's too high, they close and then it drops, and potassium helps restitute the resting membrane potential. So this is basically the essence of the Hodgkin and Huxley model, and this is what I hope you're going to do now upcoming in the project. So I'd suggest, what do you think? Like, shall we break out rooms now and have you guys like I'm gonna break out, say, 4 rooms, and you can self-assign as you like. I'm also opening this moment now for questions. I'm going to upload these slides into Canvas if they aren't yet, because I actually think I might have them in the presentation, but I'll double check. Questions? No, you ready to go?